Hi, everyone. I'm Fraser Cain. I'm the publisher of Universe Today. I've been a space and astronomy journalist for over 20 years, and we're constantly reporting on various topics in space and astronomy. But I like to bring you behind the scenes, talk to some of the people who are actually working on the technology. And today I'm excited to talk to Franck Marchis. Dr. Franck
Heck,
Marchis, yeah, from SETI Institute and also from Unistellar. And we have, I'm really excited actually. I've been following your work for several years. So why don't you let people know who you are and what you do?
yeah, so as you say, my name is Franck Marchis. I'm a researcher at the SETI Institute. I'm a planetary astronomer. I design instruments for ground-based telescopes, essentially using adaptive optic systems to study asteroids and the search for exoplanets. I'm part of the GPI project, for instance. But on the side, I'm also an entrepreneur, and I'm a co-founder of Unistellar, a company which design telescopes, digital smart telescope like this one here. And with these telescopes, we can do science. We can do basically transform everybody into an astronomer. And that's why SETI Institute is a scientific partner of the company as well.
Okay, well, I definitely want to talk about the eVscope and Unistellar, but I want to start with adaptive optics. How much has of a difference has adaptive optics made to the field of ground-based astronomy?
A lot. Last week I was at Space Telescope Institute and I gave a talk, and I think I blew everybody's mind by showing
Well,
what we can do now with
well,
adaptive
blow ours
optics.
then.
Sorry, yeah, because with adaptive optics now you can observe invisible, so you take full advantage of the size of the large telescopes, so you get better resolution than Hubble Space Telescopes. And so we have, for instance, picture of asteroids. You've seen that probably of Pallas, where you can see the craters and the central peak of the crater on an asteroid. I mean, when I was a student, adaptive optics was barely correcting the atmospheric correction, and we could barely see a point becoming sharper. Now we are reaching a moment in the technology where we can compete with space telescopes using those adaptive optic systems.
What is the state of the art? Like, I think people are roughly familiar with how adaptive optics works. You're firing a laser into the sky to create an artificial star. You're using that as a guide to tell you what the atmospheric distortions are. You are changing the mirror to adapt to that. What is the state of the art? Like the most either one that's being built right now or one of the most complicated ones out there or most sophisticated. What is the scale of this technology now?
So right now we're entering in a phase where people are building extreme adaptive optic systems. So those are capable of getting a wavefront correction like if the telescope were truly in space. Okay, so you get the same image quality, I would say. It's a simplification. I can talk about stereo ratio and so on, but I think we're gonna lose most of the people here. It's
Yeah,
not
yeah.
important.
Well, you'd be surprised. They're very
So
technical, but
if you remember, previous adaptive optic system was reaching a stereo ratio of 40%. The new one get a stereo ratio of greater than 70% and sometimes 80%. So that means they get truly the full angular resolution of and the stability of a telescope, like if you were in space. And we also improve that. We get that better because we have better mirrors. Those mirrors that move now can move 1,000 times per second. They used to do that 100 times per second. We have new technology. We know how to build high capabilities chronographs, for instance, to be able to see the surrounding of a star and see planets. So there is three, and I will say that I'm sure someone's going to correct me, but in my mind, there is three extreme adaptive optic systems so far. There is GPI, which was at Gemini South, and now is going to Gemini North, the Gemini Planet Imager, which discovered the first Jupiter's-like exoplanet, 51 Eridani b in 2015, and we have Sphere. Sphere is now finding a lot of exoplanet, and he has this system working invisible that I use for my asteroid research. And then we have SCEX-AO at Subaru. Sphere is at the VLT, SCEX-AO is at Subaru telescope in the Northern Hemisphere. And each of them kind of compete. They all want to find, of course, the smallest, the most interesting exoplanets, but they all limited so far to the detection of Jupiter, Saturn-sized exoplanets. We are going to start building telescopes that are going to be able to detect Earth, Uranus-sized, and then Earth-sized exoplanets. ELT is one of them. So what we're learning right now with this 8-meter class telescope is going to be applicable and scale up on these large telescopes. And we will be able probably to detect Earth-sized exoplanet using those telescopes.
I mean, these Sphere and the Subaru and Gemini, these are like pathfinders, prototypes for what's coming for the extremely large telescope, a 39-meter telescope. I think space telescopes are always great, but ground telescopes have always had these other advantages that you can service them, you can upgrade the instruments, you can swap out the instruments for different instruments. People can go and see them and appreciate them, hug them. Do you think that ground-based telescopes have reached parity, at least in the visible spectrum and maybe near infrared, to space-based telescopes at the same cost? Or do you think there's still some advantages?
In the near infrared, yes. In the visible, we're still starting this, of course, but it's getting there. I would say that in 5 years, we will have adaptive optic system in visible that will work on every large telescopes, and will be capable of compete with the Hubble Space Telescope. And I think that's one of the reasons. Hubble is a great facility, has been a great facility for 20-ish years. But right now, the main advantage of Hubble is the fact that it can observe in UV. Mm-hmm. And we cannot from the ground because of the atmosphere.
Yeah.
But soon, Hubble will be a desert instrument. There is no doubt about that. And it's already the case, I would say. But we still have a good stability of the PSF with Hubble Space Telescope, which is important, that we don't have yet from the ground. So we're making progress. And the advantage of ground-based telescopes is the fact that we can go there and tune the instrument, install new things. I mean, SCEX-AO is an amazing AO system with a multiple instrument suite. And we're testing new technology, which seems to be extremely exotic, but they're probably going to be the one that one day will provide a picture of another pale blue dot.
Yeah.
That will come from a ground-based telescope.
Yeah, and I think about the capability of something like the extremely large telescope at 39 meters, equipped with this really powerful adaptive optic system. It's going to change everything in our understanding of the universe. Amazing stuff. Now, do you see adaptive optics coming down? You spend a lot of your time thinking about consumer side of scientific instruments. We'll talk about this a bit in a second. But do you see adaptive optics coming down to the point that people can get some version of that installed on their own telescope?
Yeah. I'm already thinking about this, of course.
Oh, good. You just have to have a laser shooting out from your backyard telescope.
There will be a version without the lasers. But there is now prototypes and companies that will basically provide adaptive optic system at low cost I would say, less than $10,000 for amateur astronomers who wants to truly enjoy the theoretical resolution of the 1 or 50 centimeter telescope in the backyard. This is possible now because we have improved manufacturing. We understand better how to build those systems. We know what to correct and what not correct as well. So there will be something coming in the future. I'm betting in the next 5 years.
Great, that's awesome. All right, we'll talk about the eVscope. So what is it?
So the eVscope is a bit like it's not an adaptive optic system for amateur astronomers, but it's a telescope for everybody. The idea started simply by looking. Probably you bought a telescope like me when you were a kid, and you probably had a hard time using it. And I will say 99.9% of these kids, they basically give up and never use the telescope again, right? And then they start hating astronomy, or they think it's too complicated.
Oh, I got so many stories. I mean, I'm just gonna rant here for a second here. You're exactly right, right? The experience. I was pretty lucky because the first telescope that I bought was a 4-inch telescope on an alt-azimuth mount, and I was able to just find the objects in the sky, Saturn, whatever, point at it, and then I would just have to, make these diagonal changes to the telescope as the object was moving through the field of view, and then I was able to get an actual, angled mount, and it had a little knob on it. I can turn it and stay on track, and so that was fine. But then when I got a more modern telescope, one that actually had like electronics and you had to do polar alignment, I gave up. I was just like, forget it, right? I'm just going to use this thing manually because you're spending 30 minutes. You got people waiting like, oh, are we going to see Jupiter now? And you're like, yeah, just a second. Okay, now.
And then they go.
And then they don't, because your polar alignment fails. It doesn't find its. So I know precisely what you're talking about.
So everybody has this experience, right?
Yes, everybody does.
And one of my problems is that this has been kind of a problem we had for like 40 years-ish, even more, and nobody have solved that. So the eVscope is solving this. That's one of the things we do. Okay, you take the telescope, you put it in your backyard. You just have to make sure it's flat. Okay, that's not that. That's someone can do that. The kids can do that, and then you connect your telescope to an app, and the app will guide you. So you have to first press a button so the telescope will move slightly down, and then you do a place scaling. We call that a field detection because it's super fast. And in less than 2 minutes, the app will ask you what object you want to observe and calculate for you objects which are observable in your area where you're located at the moment. So you don't have to go through gigantic catalogs. You probably know those gigantic catalogs we had in the past, these big booths. Okay, and go online and look at all these things. That what can I observe tonight? It's way too complicated.
Yeah.
But you have like the most seen objects like Orion Nebula, the Triangulum Galaxy, the Dumble Nebula. They come first, of course, because they are the most iconic object in the sky. You press Dumble Nebula, the telescope will move to the location, check, tells you I'm ready. You press a button called Enhance Vision, and the system will basically take observations for you. So inside there is a digital camera at the prime focus here. Okay, and there is a computer on the side here that calculates in real time the best image possible by stacking, derotating, aligning, removing, filtering, background subtraction, all of this. And then in the eyepiece here for the Equinox 2, you see the image being built basically as the photons come. And you can see them as well on your app.
Right. And
you can share the image. Right. And multiple people can come, and instead of freezing themselves in line waiting to be able to observe, they can just connect their phone to the telescope, and they all can enjoy together observing the observing. So that's the main idea.
Yeah, and so like the technology, I think that the stroke of genius here is incorporating the plate solving into this process, because even the modern telescopes that you can get with some kind of automation, you can give it your location, which is important, because really, you need to know the telescope needs to know where it is on Earth, and then it needs to know what it's looking at. It's easy to give it the location on Earth, just put in your GPS coordinates, and now the telescope knows where it is. The tricky part is for it to understand how it is in relation to the sky, and that's why you go through this process of polar alignment. And so if I understand correctly, you just take this telescope, let it look around at the sky, it sees a couple of star fields, recognizes the star fields, does the math, the plate solving, to figure out precisely how it is oriented, and you collapse that entire process of trying to understand, trying to get the things all lined up nicely into just a completely automated experience. How long does it take from when you take this telescope and you set it out on your patio and you press the button, beep boop, let's start doing some observing, to when it's ready to start taking images for you?
2 minutes.
2 minutes. Oh
And
my God,
we
2
did
minutes.
some small competitions
Yeah.
with observer. And I know that I can do it in 2 minutes because once I wanted to observe an occultation. And I was with my student at the time, Daniel, and we were set up. And then some cops came and said, "You can be here, sir," because they thought, I don't know, we were doing something illegal with a weapon or whatever.
Yeah.
So we took the telescope, we ran out, and we set it up 2 minutes before the occultation to another place, and we observed it.
That's amazing. That's amazing. And then the second part is this idea of essentially doing the astrophotography for you. And that's the other whole, like, let's say you are able to get your telescope to the point that you can go out, take it out, spend your 30 minutes polar aligning it. You're looking through the eyepiece. You're seeing Jupiter where it's supposed to be. You're punching in to go see the Orion Nebula. That's all working. But then if you want to do astrophotography, it's a whole other rabbit hole level of complexity to try to go into about getting your camera cooled down and getting the right filters in place and getting the right exposure lengths and getting the images all downloaded to your computer and then processing the images locally and removing the ones that have the Starlink going through and so on and so on and so on, right? It's a whole other level of misery. And it takes those two like together to take just a picture of the Orion Nebula.
So I'm gonna go back to my example of the kid here because this is something I really, when you buy a telescope to your kid, you will receive the telescope, and if you look at, I'm not gonna say brand name here because I don't want to keep neutral, but most of those brands, what they put is a pretty picture of a galaxy or nebulae taken by Hubble Space Telescope on the box. Right?
Yes.
So imagine the kids finally managed to magically align the telescope, calibrate, focus it, observe Jupiter and the moons, fun, and then say, "Oh, I'm going to observe a galaxy or nebulae." Find the nebulae, which is already complicated for most people, right? And what you see is a tiny grayish dot. Basically.
Yes, a little blur, a smear.
A little blur. You call your friends and you say, "Hey, I found the galaxy, and this is tiny blur," and you have the box still, and you can see the beautiful picture of the galaxy on the box.
Yeah.
That's a high disappointment. It's creating a generation of people who hate astronomy. That's what we have been doing for the past 50 years, I would say. So with this telescope, we're trying to break that. Yes, the image is not like the best image you can get doing astrophotography on supercomputer, aligning, and all of this. I truly admire people who do that. It's a very complex problem, and we are improving our image quality, but yes, you see a galaxy. I mean, when I showed the spiral galaxy to my kids for the first time, they're teenager, so they have an attention span literally 5 seconds. They were absolutely impressed by the fact that they could see the spiral arms of the galaxy, the triangulum galaxy, and they realized that they are seeing something far away with billion of stars inside. And I think it's a game changer for the psyche of people, and that's what we were trying to provide with this telescope, a tool, an extension of human being to reconnect to space and to astronomy.
Yeah, like like you take a telescope, even like a nice Dobsonian, and you look at the moon or Jupiter or Saturn or Mars, and they all are exactly what you were hoping to see. They are as beautiful and amazing, and it's kind of stunning that you're looking into the eyepiece and you're seeing the rings of Saturn. And if you've got even just a 6-inch telescope or an 8-inch telescope with a good Barlow on it, and you're seeing those rings, it is like nothing else. But once you've looked at those 5 things, and then you're like, what's next? Okay, globular clusters and open star clusters are wonderful to look at inside the telescope. But apart from that, nebulae, maybe the ring nebula, but really nebulae and galaxies are disappointing until you do those big, long exposures. And those are 95% of the things, 99% of the things that you're going to want to look at once you're tired of the moon again. Right? So, so then what, sort of thinking of, from an astrophotography perspective, let's say people are fairly familiar with astrophotography. What is the telescope doing to actually build up that image?
So we do what professional astronomers have been doing for years. Okay, so we do background subtraction, some kind of flat fill, but pixel correction, the rotation, stacking, filtering of the image in some cases. We also remove the image when there is no, I don't know, if there is wind, for instance, or people walk around the telescope and the floor is not stable. The telescope recognize that, detect this, and get rid of those frames. So try to improve the frame, warn the user that the floor is moving. And then we do simply stacking. And I mean, we have our own secret sauce as well that I'm not going to reveal here, of course, but we have our own algorithm to improve even the image better. The detector is the temps detector you have on the camera with Bayer matrix. So basically, you have colors thanks to that. And that's the reason you see the nebula like the dumbbell in color. You can see the green and the red without any problem with your eyes into the eyepiece or on your phone. So the principles are very simple, I would say. There's nothing really, but we have our own algorithm in the back. But it's improving. You may know, I don't know if you have noticed, the images get better over time. We released the first telescope in 2019, and now 2022, you can see that the images are getting better because we are improving the algorithm. We are learning as well how people use our telescope. That's also one of the best things of this telescope, is that because they're identical, we truly understand the limitation or the property of the detector and the way the detector behave or the way the telescope behave. So we're building algorithm around that to improve the image quality as well. And there will be more coming. Every month we change the app and there is some improvement.
Well, I mean, when I think about my experience with astrophotography, you realize how much it is an art as much of it is a science and as much of it is a technology thing. And you can see people who get into the field and they show you their first picture, and 2 years later, it's still the same camera, the same telescope, but the new pictures are dramatically different. They've learned to observe when the seeing is really good. They've learned to better dial in the exposure times to the object for what it is that they're looking at. Some objects like a long exposure time, other objects are fine with shorter exposure times, so you don't, say, blow out the bright parts of the trapezium in the Orion Nebula. How much control, like as you become more advanced and more skilled, how much control can the photographer get to start to apply their skills and ideas into this final image that they're creating as they're gathering raw data?
So for the eVscope, right now, the software decide basically the gain and exposure time of the object you're observing. This is something like we set automatically, and then you have access to your data if you want to do your own data analysis and your own astrophotography.
Like, is it just FITS files?
It could be FITS or something else, but since I use FITS only, I don't care about the name of the other one.
Right, okay. But you get, so in other words, you can download all the FITS files that the telescope was recording, and then you can bring them over into Nebulosity or whatever you want to try and stack up your image yourself. Okay, so cool.
We are not to the point where you can download them automatically. Just to clarify, you have to ask Unistellar, but you receive that in less than 24 hours. But we are going to work on the system to make this easier in the future. Right.
Yeah, I mean, I think that's the gap. The algorithm is great, and I think you're exactly right that you get this immediate. You can't believe that this tiny telescope is taking this image and is showing you the dust lanes in Andromeda or whatever. But a skilled astrophotographer is going to say, I could
That's
do
not
better.
enough.
It's not enough. I could do better, right? And I think that's
And we do have those, in fact, and I like them because they challenge us.
Well,
Now they show us that what we can truly get with our telescope. And sometimes I'm even surprised myself to see the quality of data they get. So yeah.
right. So then, I mean, that's a little weird that you have to email and ask Unistellar for the data. I mean, is the data owned by?
No, the data owned by the users. We have to follow the GDPR
Right.
rules. So the only reason we have to ask Unistellar is because you have to send the data to us. So then they are on our server.
Right.
And people ask, why do you care to receive data from the users? So first of all, to clarify, the users, they don't have to send us the data. If they don't want to, they don't. Right. And that's fine. But if they want to receive the data, they have to send it to us, definitely. Yeah. The reason we like receiving data as well is because we do a lot of analysis about the observations, and we see how many, what people observe. We understand better the behavior of the telescope. All those algorithms that I mentioned to you to improve the image quality over the past 2 years, they came out because of that, because we received the data from people and we kind of better understand what's going on with the telescope.
Right. Yeah. I mean, it feels to me like the experimentation done by the users to change exposure times to depending on the object. I mean, that's like the biggest thing that I would think of is like the technique to get a good picture of the Orion Nebula is very different from the technique to get a good picture of the Cigar Galaxy.
Yeah.
And
keep in mind that the true goal of Unistellar is to democratize astronomy. Mm-hmm. So basically what we would like is that people never have to think about what you just mentioned. Mm-hmm. All of this should be automatic, should be done by the processor on board, and the computer know what you're observing and adjust the image, adjust the gain based on that. That's ultimately our goal, in fact.
Yeah.
I would like people to have a telescope that they can enjoy looking at the sky. Like when you use a phone, you don't care about how the photons are generating on the LED screen. You don't care about all of this. You're using your phone to communicate with your friends and your family. Well, you should use a telescope to enjoy the dark sky, to admire galaxies and nebulae, not tuning around and trying to get the best. I mean, it's great. A small portion of the people will love to do that, but that's not everybody. And what we're trying to do is to bring astronomy to everybody.
Let's talk about the science of using the eVscope. What are some of the, I guess, as your role as a scientist, what kinds of observations and campaigns have you been organizing to get eVscope owners involved in?
We have a lot. So I'm going to drop you some numbers here. In the year 2021, we observed 400 exoplanet transits. And those are transiting exoplanet, Kepler, or test objects of interest that's Jupiter size orbiting around G-type stars, typically. And we detect them, the 1% attenuation using our telescopes. We combine observation with multiple users around the world so we can see very long period planet, for instance. For instance, yesterday we announced the detection of HD 80606b, which is one of these extremely eccentric exoplanets. I think it's one of the most eccentric orbit. And this exoplanet also transits, which is kind of fun when you think about it. And of course, this is going to be one of the targets of the JWST ERS program.
Yeah, I saw that press release just like today. Yeah.
So what we asked as our user, we predicted when the occultation will happen in December 11th. Yeah, there was an uncertainty of 2 or 3 hours. And we asked our user to observe it continuously. So we have users all around the world, Europe, United States, Japan, because it was Northern Hemisphere, who observed it. And you can see the visual animation, we can see the attenuation. And this is possible because of the Unistellar network, because we have a distributed network. We have 7,000 telescopes around the world at the moment. Most of them are in North America, Europe, and Japan, but now we are growing the network to other regions of the world. And they observe this, the exoplanet transit. And it's important to have observed that now, because now we can estimate to the order of 3 minutes, I think the error is 2 or 3 minutes, when the transit will occur, when JWST will observe it in October.
Huh. Interesting.
So we save time,
Right.
JWST time.
Right. So JWST can just observe the exact 3 minutes and then move on to some other important job.
Exactly.
Right.
Extragalactic people should be happy. We're gonna save time of these precious telescopes so they can observe more galaxies.
It is interesting. Like there are, I mean, at this point, probably 10,000-ish objects of interest between Kepler and TESS and other ground-based observatories, more coming all the time, with 5,000 confirmed exoplanets. There's a lot of work to be done to image these objects of interest and provide more confirmation, and not enough telescopes to go around, and not enough astronomers to do this work. What percentage do you think of these could be confirmed by, say, an eVscope? Like if I just donated my eVscope time, I just set it outside and let it just work on science for the night, how much of a role do you think these telescopes could play in just, say, exoplanet research?
So in TESS, I don't have the exact number, but Tom Esposito, who leads this program, told me last time that he knows that there is at least 800 target of interest that we can observe with the eVscope right now. TESS object of interest, sorry. So that's a lot. That's more than one person can do. Every night, there is one. Every night, there is a planet, a TESS object of interest waiting to be confirmed, in fact. And we don't have enough telescopes for that. So we are starting this. We're working with TFOP, the team, and we are basically confirming some of those exoplanets. We have our first TFOP had been submitted last week, in fact. It's a confirmation of a planet, and we also see a shift of the timing of the planet. So now the orbit has been refined, and it's a confirmed exoplanet. So yeah, and those people, I would say, who have this telescope were not astronomers before, and most of them, half of them, had never had a telescope before, even. So
what do you think the future, or what are some? I mean, that's just one, exoplanets, but I mean, you've done asteroids. What are some other observations?
So after that, we do planetary defense. So we basically have a robot, analyzing continuously what comes from MPC and tell us when there is something observable. Like if you find an asteroid is found now, and we know that tonight it will be observable from California and fly by Earth, I will be able to send this alert to our network. And we have observation taken regularly in planetary defense to refine the orbit of those asteroids. This is very challenging, especially with such a small aperture. But once again, the point here is that there will be always someone observing this night. So there will be always one person at least to observe this asteroid and be able to refine its orbit. And it's very valuable, as you know. We will know if, for instance, the asteroid impacts Earth in the next hours, having the last points is extremely important to accurately estimate the location of the impact. At the SETI Institute, Peter Jennings Cain have done that in 2006, and we get a pristine meteorite in Sudan thanks to that. We went to Sudan a month later, and we captured fragments of an asteroid, basically almost unaltered.
Yeah,
that's this kind of stuff that we will do. We want to contribute to that kind of science. We do occultations as well. So those are when the asteroid is passing between us and the star, and we see the shadow. And here we need to have multiple observations taken at the same time, roughly, and we see the shadow of the asteroid. We target main belt, large main belt, because there is still a lot of them. We don't know the size and the shape, which is kind of surprising. And we also target loose emission targets, Trojan asteroids. So we observe the first occultation of Horus was observed from Oman using the Unistellar network. And that's allow users a month later to observe again an occultation in Hawaii, in Big Island, precisely, because our data pinpoint the exact location of Horus.
What are some ideas that you haven't had a chance to implement yet that you
Oh,
think would work?
so we want to do comets, and in
Mm-hmm.
fact, I hired a new comet researcher, Ariel Grelotsky from UCLA. She's coming to join our team, and she's going to be working on how we can use our system to observe more comets, derive the spin orbit, the spin of the nucleus from the jets, analyzing the jet, for instance. We can put filter in front of the eVscope. That's something I can mention briefly here. So that we could find the right filter to improve the contrast. I'm going to Namibia in June to observe an occultation by Europa. And here the goal is to precisely pinpoint the location of Europa. So we have some constraint on the interior of Jupiter. So that's another type of occultation of satellites, by satellites. Of course, there is some more interesting things we are thinking about, like supernovae. We have now an advisor in this field that's going to help us developing the supernovae field. And we have more challenging stuff. Like one of them is to try to find the afterglow of gamma ray burst, or even the afterglow of gravitational waves.
And with a 4-inch or just over a 4-inch reflector telescope and optics on board. Yeah.
Because we can combine observations. Remember that.
Right.
They're all identical, and we have learned a lot about the sensitivity of the telescope. So there is a paper written by Richard Berry, which is in preparation. I can mention that we have now a limited magnitude of our eVscope, which is 17.5. The details, survey, the SNA, etc. So just with this telescope, you reach 17.5. We have combined observation with 20 users, and we reached 19.5. Okay.
Yeah. Yeah. I
so
mean,
now,
like there's this idea, like when people learn about, say, interferometry and how you can have two telescopes on opposite sides of the planet working together to act like a single telescope, they're like, whoa, could we do that with regular telescopes? And the answer is no, unless you can align them to within nanometers of each other, make always sure that they are. It's very tricky to do, but you can combine the light as if it was the two telescopes, the total size of the two mirrors acting together. And so are you saying like if you take all however many thousands of these telescopes out there and you all point them at the same object at the same time, it's kind of like one telescope with the combined surface area of all of those telescopes added together?
Yeah. Especially when the telescopes are strictly identical and you truly understand their behavior in cities with high background, vibration, winds, and so on. That's really what you need to know.
Right.
This is a research that we are starting now.
Yeah.
We have done some tests with comets. We have observed a comet. There was a comet Atlas, and we saw the comet basically disintegrated thanks to our users, citizen astronomers. And this observation was taken with 20 and 40 citizen astronomers simultaneously. And we can see that we reach a magnitude 19.5 without any problem.
Which no one telescope should be able to reach.
Yes.
That's amazing. Wow, that's
amazing,
crazy.
Yeah,
that's really interesting. Yeah, there was a great idea for a space telescope that I saw a couple of years ago where they were just following on this idea. Like, instead of trying to build an interferometer, let's just build really inexpensive telescopes. Let's just, like, inflatable telescopes. Let's just put them up one after the other, and you get the combined light gathering power of all of those telescopes. Not necessarily, you're not going to get the interferometry aspect of it, but at least if you send up two 1 meter telescopes, now you've got a 2 meter telescope. You send up 1,000, now you've got 1,000 meter telescope. Then eventually this does add up. And it's interesting to see, as you can get advantage to all of these telescopes working simultaneously, that you can start to do more sensitive instruments. Now, I've heard that there really is a limit. Like, beyond a 1 meter telescope, without adaptive optics, you really can't improve your image of the sky.
Yeah.
right? Like
The
literally
resolution
just
will always stay limited to the size of the aperture. That's
right.
correct.
Yeah, and even if you had a 10-meter telescope, it wouldn't be able to take a much better picture than a 1-meter telescope without adaptive optics. Is there some advantage to be made on seeing the sky from different atmospheric conditions around the world? Like if the one telescope is in France and the other one is in the US, they're seeing different versions of the atmosphere. Is there a way to then get a sense of the ground truth between those two observations?
No, there is, to my knowledge, there is none. The reason for which, however, it's interesting to have multiple observers around the planet observing almost simultaneously a phenomena, for instance, is that the atmosphere changes a lot. And you sometimes, even in San Francisco here, I've seen seeing, which are better than 1 arc second. Okay.
Right.
So it's possible in cities. So the more people observe, the more likely you will get a very good set of observations.
Right.
If you have 1,000 telescopes observing, let's say you take the 10% best image, you will reach and you will get an image quality which is significantly better because you have selected the one which has the best C.
But I wonder if the one can tell the others to improve their seeing. Like, I don't know. I mean, I may be way out of,
Yeah, no.
Like,
the problem of it's
like
a Kolmogorov thing, so it's very it's chaotic.
For sure.
There is no, yeah.
I think about, like, say, gravitational lensing and how you can reconstruct the image of the galaxy that you're seeing through the gravitational lens. Could you reconstruct the image, the bad images that are still gathering some photons? They're just they're photons in the wrong places. And I wonder if you could use the best seeing, almost like wisdom of the crowds, to try to improve the overall images. But it might be impossible.
It's probably possible to use this good image as a prior when you do data analysis like deconvolution or machine learning. Basically, you tell the algorithm, we know there is something here, faint. We see it in the good data. Take all those faint, crappy data, and try to get extracted.
That's what I'm saying. Yeah,
it's possible.
Yeah, interesting.
In fact, that's the principle of deconvolution. Using the Mistral algorithm for those who really wants to know all the details, and that's what we do when we analyze our observation using the sphere adaptive optic system.
How much does an eVscope cost?
So the Equinox version, which is the one here, is 3K.
Is 3K?
Yeah, 3K. And this one here, that's the eVscope 2, is 5,200 at the moment.
Okay. And is it the same size telescope? So it's the same 4-inch-ish reflector in both cases.
Yeah. So the difference between those two is this one has a detector which resolution of 4K, this one 7K, and this one has an eyepiece, which this one does not.
Right. So for the people who do want the eyepiece and you do want to just look and see Saturn and see Jupiter, you can see it in real time as well. So the complaint, obviously, is that I can go out and I can buy a pretty good astrophotography rig for a significantly lower price than that. And the misery that goes along with what we talked about earlier on. So how do you make the case to people, like, who is this for? Because that's a lot of money. $5,000 is a lot of money for a person who wants to see pictures of the night sky. That's a serious investment. If you're going to spend $5,000 to take pictures of the night sky, you might be really tempted to spend that on old school polar line, wait, I'm just trying to get the picture, wait type gear. Who do you think this is for?
So we have a lot of people who buy this telescope, right? I mean, we have reached a network of 7,000 people. So there is interest from the community to buy telescopes like that. The Equinox, which is the low-cost one, is, in my mind, for people who want to be part of the network and do science, really. The Equinox is the best instrument if you want to be part of the citizen science network of Unistellar and you want to, from your backyard, be able to observe galaxy nebulae and do a meaningful astronomy. And you learn as well. You can access to the data. You can also process your own observations and be part of the network. The Equinox 2 at 5K is truly expensive. It's an expensive instrument. Yes, the eyepiece, and I will say that a lot of amateur astronomer club is buying that now, because as you know, when you do astronomy and you set up a telescope, people are not patient. They don't wait, especially the younger generation. So they want some instant gratification. We are providing this with this telescope. Schools, community colleges, universities are buying these telescopes. They're replacing, in fact, the old telescope they had in the dome that students could not use because they were too complicated. Now they use the eVscope 2, and they do scientific investigation as well with the teachers. So we have a lot of education also that I will not talk about today, but we are building an education program around the eVscopes. And we are providing material for educators, material for professors, so they can be part of the network, do science with their students, learn how to process and analyze data. So it's an investment, but if you buy a telescope, you build it yourself, you need a computer to learn how to process, it's gonna at the end be almost the same price. Someone make a comparison, I forgot, it's published somewhere online, of the price, and at the end you will see that you will be more or less the same. The cost is more or less the same. So it's just, if you have a lot of time, yeah, do your own telescope, build your own,
grind your own mirror.
Yeah, polish your own mirror if you really, really want to do everything. Yep. But in my case, I have a job as an astronomer, and since I have this telescope, you see there's 3 of them around me here. It's not for the show. They're always here.
Right.
Always, because last night I tried to catch comet C21 2021-03, which is just coming out of the sun, hoping to be able to detect it. I use those telescopes. Almost every week I use my telescope 3 or 4 times. Mm-hmm. And I get a lot of comments from people telling me that in the 6 months they had this telescope, they use it more than they have used the old, I'm not saying brands, telescopes in the past, because it's easy to use, because it's simple, because it doesn't have all this complexity, and it takes 2 minutes to taking out. So in the evening, you see the sun is setting, and it may be a beautiful night. You take your telescope out, you observe for 1 hour, and then you go back home and you watch Netflix, whatever you want. But you have this moment where you connected with the sky.
The saying with a camera, right, is the best camera is the one that you use.
Exactly.
And I absolutely have a telescope that is gathering dust, that I don't even want to think about how much work it's going to be to get it out each time and polar align and take images. And instead I take my binoculars and I go outside and I lie in the easy chair and look at the sky with binoculars, because it's easy. It's quick. So what do you see as the future of this kind of a solution? I'm sort of surprised, though, that, I mean, it feels like an easy connection to go to, like, I could just bolt a RASA on top of the mount while it's doing its work, and the RASA could just tag along with the plate solving. Why hasn't this idea of plate solving and automation been brought into the more traditional, the old school telescopes? It doesn't feel like it's that complicated now that you're demonstrating that this is possible and make a best of both worlds.
Yeah, most of the time the idea is simple and just nobody got the idea before. Okay.
Yeah.
There is one thing that I went to Marseille 2 weeks ago and I talked to my colleagues about this, and one of the engineers told me something which I think it's in my mind now. It's very easy, not very easy, but it's easier to do an instrument that works 90% of the time, like do plate solving and it fails 10% of the time and you tune it, etc., blah, blah. But it's very complicated to do an instrument that works 100% of the time. And the eVscope does work 100% of the time in terms of the plate solving, the data analysis, etc. If you want to sell a product to people, telling them that it's easy to use and it's fun, it really needs to be easy to use and fun and works all the time. Go back to the iPhone comparison. There was a ton of iPhone before iPhone. You probably remember that. They were like complicated to use, very like heavy. There was all this complexity that was unnecessary. And this guy came, Steve Jobs came and said, we're going to do something simple, slick, an iPhone, very simple. And it does work all the time. And the first one was extremely expensive, by the way. So you probably remember, it was a few people could buy an iPhone. And now you go walk in the street, and in the US, 50% of the people work with an iPhone in their hand.
So I mean, guess, do you see this technology taking over everything? This method, starting with making the telescope the one you want to use, and then increasing the power and complexity and capability and so on?
I think so. Because the best telescope is the telescope that you use.
Yep.
And the best telescope is a telescope where you can bring people around and have fun and discuss about star and galaxy and the search for life and the existence of aliens. That's the best telescope. The best telescope is not the one that's going to allow you to observe a quasar at the redshift of 7 and show after 2 hours a tiny dot to your friends. They will not care that much.
Or the one that your laundry hangs from.
Yeah.
Right.
Exactly.
Yeah. Frank, if people want to find out more about the telescope, where's the best place to go?
So the company Unistellar has a website called at unistellar.com. And you can also go to the SETI website for the education part. In the education, you will find some of the material we provide for educators. So, and I mean, the best is really also if you want to see the telescope in action, you can also go on our YouTube page. We have explanation of how the telescope works, unpacking, aligning, focus, and all of this. So people will have an idea of the complexity of the telescope and if it's truly for them or not.
I wonder how well it would work for the virtual star parties. I don't know if you know, we do these nights where we
I participated to one of them 2 years ago.
Right. Yeah. So I wonder how well, if we could like live stream from one of these into the star party.
We observed a supernova at the time.
Yeah.
I will always remember because it's another observation when the cops came to speak to me. So, I'm like, I don't know, I'm jinxed.
Yeah, maybe.
In the middle of nowhere.
Yeah.
You're sure that there were cops who just come to speak to me, ask me. And he came just after the live.
That's crazy.
He was nice. He was very curious. He wanted to see what I was doing on the parking lot. So.
Yeah, it's funny. We've again had to put the star parties on hiatus because of this reliability, dependability, weather issue, number of people, etc. Like, I just can't solve this problem. I can't figure out a way to get a lot of people around the world to come together who will have reliable weather to be able to show off the night sky. So I don't know, maybe you can help me figure this out at some point.
Well, the 5th of May, we are doing an event at the California Academy of Sciences in San Francisco, but we're asking several of our ambassadors across the US to use their telescope, and we will be streaming live. So if you look at the website, our website or our social media, you will find a link so you can see the telescope in action.
So maybe I'll tap into some of these people and see if they can join up. That would be a good idea.
And you can even ask for objects if you want to.
Well, that's what I'm talking about. Yeah. So if people want to follow your work, what's the best way to do that?
Also go on the SETI.org page, and you will see some of my news. But my social media, I'm very active on Twitter.
Yep.
So that's where you're going to see most of my work, in fact.
Fantastic. Well, Frank, it was a pleasure to talk to you again. I'm glad the cops didn't show up this time to shut this down. But good luck with what you're doing, and I look forward to sort of the future of this part of the hobby and as it connects into science. It's pretty exciting stuff. So good luck with everything you're working on.
Thank you very much, Fedor.
All right.
Thank you for having me.
All right. Take care.
Bye-bye.